Welcome to our video on cylinders and quadratic surfaces. In this lesson, we'll explore three-dimensional surfaces described by equations, focusing on cylinders and quadratic surfaces. We'll go step by step through the key concepts, standard equations, and visual representations of these important mathematical objects. Let's begin with cylinders. A cylinder in three-dimensional space is generated by taking a plane curve, called the directrix, and extending it along a straight line, called the axis, that is perpendicular to the curve's plane. For example, if we have a curve in the xy plane given by f of x, y equals 0, then the cylinder with axis parallel to the z-axis would be described by the same equation f of x, y equals 0, with z ranging over all real numbers. This means the surface looks identical no matter what z value you choose. Let's look at common examples of cylinders. First, we have the circular cylinder with radius r. Its equation is x squared plus y squared equals r squared, where z can be any real number. As you can see, all cross-sections parallel to the xy plane are circles of radius r. Next, we have the parabolic cylinder, whose equation is y equals a times x squared, where z can be any real number. Its cross-sections in the xy plane are parabolas. Finally, we have the elliptic cylinder, with equation x squared over a squared plus y squared over b squared equals 1, where z can be any real number. Its cross-sections are ellipses. Now, let's move on to quadratic surfaces. A quadratic surface, also known as a second-degree surface, in three-dimensional space has a polynomial equation of total degree less than or equal to 2. The general form looks like this: ax squared plus by squared plus c z squared plus dx, y plus ex z plus f y z plus gx plus hy plus I z plus j equals 0. By rotating and translating the axes, we can simplify these equations into standard forms. We'll look at 6 common types of quadratic surfaces. The first quadratic surface is the ellipsoid. An ellipsoid has the standard equation x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, where a, b, and c are positive numbers. An ellipsoid is a closed surface, similar to a stretched or compressed sphere. All cross-sections by planes through the origin are ellipses, or circles if two axes have equal lengths. If at equals b equals c, we get a sphere. Next, we have the elliptic paraboloid. An elliptic paraboloid has the standard equation x squared over a squared plus y squared over b squared equals z, opening upward along the positive z-axis. The horizontal cross-sections, where z equals a constant, are ellipses. The vertical cross-sections through the z-axis are parabolas. This shape resembles a bowl or a satellite dish. The third quadratic surface is the hyperbolic paraboloid, often called a saddle. A hyperbolic paraboloid has the standard equation x squared over a squared minus y squared over b squared equals c. Cross-sections by planes where z equals a constant are hyperbolas. It's a doubly ruled surface, meaning it contains 2 families of straight lines. The hyperbolic paraboloid has a saddle shape, curving upward in one direction and downward in the perpendicular direction. Next, we have the one-sheeted hyperboloid. A one-sheeted hyperboloid has the standard equation x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. The cross-sections where z equals a constant are ellipses when the absolute value of z is less than c, and hyperbolas otherwise. This is also a doubly ruled surface. The one-sheeted hyperboloid looks like an hourglass that extends infinitely in both directions. The fifth quadratic surface is the two-sheeted hyperboloid. A two-sheeted hyperboloid has the standard equation negative x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. This surface consists of 2 disjoint bowls, or sheets opening along the positive and negative z-axis. The cross-sections where z equals a constant are empty when the absolute value of z is less than c, and ellipses otherwise. The final quadratic surface we'll discuss is the cone, specifically the quadracone. A quadracone has the standard equation x squared over a squared plus y squared over b squared minus z squared over c squared equals 0. This is a doubly ruled surface with its vertex at the origin. The cross-sections where z equals a constant are ellipses, or specifically circles when it equals b, for any z not equal to 0. Through the vertex, the cross-sections are pairs of lines. Let's summarize what we've learned about cylinders and quadratic surfaces. A cylinder is formed by extending a plane curve along a line perpendicular to the curve's plane. Common examples include circular, parabolic, and elliptic cylinders. Quadric surfaces are second-degree surfaces in three-dimensional space. We've covered 6 standard types: the ellipsoid, elliptic paraboloid, hyperbolic paraboloid, one-sheeted hyperboloid, two-sheeted hyperboloid, and the cone. When identifying these surfaces, you can follow these steps. First, write the equation in general form and complete the square in each variable to reach a standard form. Next, classify the surface by the signs of the squared terms and the constant on the right side. Finally, determine cross-sections in planes like z equals constant or x equals 0 to guide your sketch. With these standard equations and properties in hand, you can recognize, classify, and sketch any cylinder or quadric surface in three-dimensional space. Thank you for watching this video on cylinders and quadric surfaces. These mathematical objects are not just theoretical constructs, but have numerous applications in physics, engineering, computer graphics, and more. I hope this step-by-step exploration has helped you understand these three-dimensional surfaces better. See you in the next lesson.